4.2 is combinations. A combination is the number of ways to choose some subset R items out of N items without putting them in order. It's very, very similar to a permutation, except for that last part, without putting them in order. The formula looks kind of complicated, and it looks like this. N factorial over N minus R factorial, R factorial. Very, very similar to the permutation, but it's order doesn't matter this time. And so what you're going to want to pay attention to is that this is a group from a larger group. I guess it doesn't technically have to be larger, but a lot of the times it is, most times. A group from a larger group, and order doesn't matter. And it's kind of tough because sometimes the order that you put these things in matters and sometimes it doesn't. And so you really have to pay attention to the language. Consider a group of 8 people. How many ways can you form a committee of 3 people? All right. And so committee is kind of one of those keywords that you see a lot of the times, but the word committee is telling you that order doesn't matter. All right. If I have a committee, I've got a classroom full of people and I just want to pick 3 of them, and who cares who goes first? Doesn't matter. You 3 go to the office. Who cares who's first, right? So a group of 8, I want 3 out of 8. It's a group from a group, but order doesn't matter. So that's how I know this is a combination. And so it's going to be 8C3. And we could use this formula right here. I'd rather just use a calculator though. So on your calculator, we're going to go 8 in CR3. It's 56. I'm not putting them in order. I'm just picking 3 of them. So what about 5 people? 5 people. So 8C5. Also 56. Which leads us to an interesting conclusion, I think. If you've got 8 people and I pick 3 people to go out in the hall, that's going to be the exact same thing as picking 5 people to stay in the room. Does that make sense? The reason why those 2 numbers are the same is because it's really the same problem. If I pick 3 people to do something, that's the same as saying 5 people don't do something. And so that's why those 2 are the same. Comes up every now and then. Number 2, Jack Jackson is one of 30 lawyers at a firm. 3 lawyers from the firm are to be selected to work on a special project. In how many ways can 3 lawyers be selected? So what I think you need to get in the habit of is asking yourself first, is this a group out of a group? Am I taking a group of items out of a larger group of items? Is that what we're doing? And then you would want to ask yourself if order matters or not. Because if order does matter, it's a permutation, like last time. If order does not matter, it's a combination. So we're taking 3 out of 30, right? 3 lawyers out of 30. Does the order that they're picked matter? No, order doesn't matter. So this is going to be a combination. 30C3 is 4,060. Remember when we talk about counting, counting means how many ways are there of doing something. And so that's what we've done. I'm not going to specifically count 1, 2, 3, 4, all the way up to 4,060, but that's what we're doing. A combination is one technique for counting the number of ways of finding these 3 lawyers. Part B changes it slightly. In how many ways can the 3 lawyers be selected if Jack is one of them? Jack Jackson. Okay, so this is different, and this complicates the issue. And what I would recommend is you really, really, really try to nail down the problem into something really specific. All right. When they say I want to select Jack, what does that imply? What? All right. So yes, that's true. So let's nail this down. Jack is one of the 3, right? So we've got Jack and what? And 2 more. Very good. That's exactly what I want to say. I like to use the word and. because and reminds me of that fundamental counting principle from last lesson. When you can write it as an and or a or, all right, and means times. So to me, at this point, when I see that word and, I'm looking at it like a blanks problem. I've got to find Jack and I've got to find two more. Okay. So how many ways are there of picking Jack? There's only one Jack, right? There's only one Jack. Jack Jackson, lawyer. Now we need to pick two more. So two more, is that a group out of a group? That's a group out of a group. All right, so you want to pay attention to that. You want to constantly come back to that question. I'm picking a group of two out of how many lawyers? 29, very good. Not 30, because we already picked Jack, so there's 29 others, right? So, and two others. So we're going to pick two out of 29. Does order matter for those two? I don't think so. So this problem becomes 1 times 29 choose 2. Well, that's just going to be 29 choose 2. 406. These problems are really tricky sometimes because you really, really want to be specific and nail down exactly what they're talking about. You come back to the same techniques a lot, but if you don't really, really get hyper literal on the language, it gets confusing because am I doing this or am I doing this? In how many ways can a group of at most 3 lawyers be selected? You want to be hyper literal and you want to think about rewording the question for like your little brother or something. All right. When it says at most 3, every one of us knows what that means, but I want you to be hyper literal like you're explaining it to a 6-year-old. What does at most 3 mean? Very good. I'm glad that I heard the word or. I heard you say 1, 2, or 3, right? 1, 2, or 3. All right. But you missed one possibility. 1, 2, or 3. What's another possibility? 0. So if I'm going to be hyper literal on this, I'm going to say that what they mean is 0 or 1 or 2 or 3 lawyers. That's what they mean. When they say at most 3, they mean 0 or 1 or 2 or 3. And again, I like using words like and or when I'm trying to be hyper literal because I know or means at. And so I kind of turn this into an addition problem where I'm going to add several things here. So really, I've turned this into 4 smaller problems. This one or this one or this one or this one. I've got 4 smaller problems. I'm going to add them together. So if I want 0, if I want to pick 0 lawyers out of the 30, I mean, you could really say, well, out of the 30, I want to choose 0. Anybody know what 30 choose 0 is? Not 0, 1. It's like if I've got 30 people in this room and I want to pick 0 of it, there's only one way to do that. There's only one way for me to not pick anybody, and it's to not pick anybody. All right, so that's going to be 1, and you should get used to that fact and memorize that fact. Anytime you choose 0, it's going to be 1. Anything choose 0 is 1. Or out of the 30, I'm going to choose 1 lawyer. Well, how many ways are there for me to choose 1 lawyer? Yeah, it's going to be 30. And that's another thing that you should probably memorize. Anytime you choose 1, it's just going to be the number. Or if I pick 2, that's going to be like 30 choose 2. And I can't do that one in my head because that formula is kind of complicated. But I don't have to do it in my head. 30 choose 2 is 435. And 30 choose 3, we already did that one, right? 30 choose 3 was 4,060. 4,060. So to answer this question, in how many ways can a group of at most 3 lawyers be selected? Add those numbers together. Add those numbers together and get 4,526. Okay. 4,526. Number 3, a manager oversees 12 employees. He must select 3 employees for promotion. In how many ways can the 3 employees be chosen? So I'm always going to go back to, is it a group from a group? Am I taking a group out of a group? Does order matter? Group out of a group. I want 3 employees out of 12 employees. That's group out of a group. Does the order matter? No, this is a combination. 12 choose 3. 12 choose 3. 220. In how many ways can 3 employees be chosen for positions of assistant manager, assistant to the assistant manager, or dishwasher? Okay, so you are assistant manager, you are assistant to the assistant manager, and you are the dishwasher. Okay, does the order matter? I'd rather be the assistant manager than the dishwasher, probably, right? Okay, so the order matters this time. This is a different question. I'm still taking 3 out of the 12. But this time, since the order matters, it's going to be a permutation. Permutation, remember, is a part of a factorial. It's 12 times 11 times 10. If you didn't have a calculator, you could do this, I suppose, by doing 12 times 11 times 10. But we do have a calculator, so let's just do the permutation, 1320. So pay attention to the language. The language is going to tell you whether order matters or not. You've got to pay attention to that, and that's going to be an important thing. As soon as we get to the next lesson and they're all mixed up and you don't know which one is this order matters or not, you've got to figure it out based on the language. Number 4, 5 cards are dealt from a standard 52 card deck. How many such hands have only face cards? How many such hands have only face cards? Are we taking a group out of a group? Yeah, we definitely want 5 cards, but out of how many cards? I know how many face cards there are. King, queen, and jack of the 4 suits. This is going to be 12. So the 52 is just kind of there to throw you off for this problem. It's going to be a group out of a group. 5 out of the 12 face cards. Does the order matter from this question? No, I don't care if a king comes first and a queen. It doesn't matter. Order doesn't matter. That's a combination. 12C5. 792. Now, when you talk about cards in probability or whatever, we'll get into more probability next time. But 52 choose 5 is a really important number. 52 choose 5. That's how many 5-card poker hands there are. That's a really important number that comes up all the time, but not this time. How many such hands have a full house of aces and eights? So here's where people that don't know anything about cards kind of have a disadvantage. All right, aces and eights, full house looks like this. You've got 3 aces and 2 eights. All right, 3 aces and 2 eights, not 3 eights. But 3 aces. That's what they're saying. So ace, 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 8, 8. Okay. Think about what they're saying right here. They're saying aces and eights. So if I want to pick 3 aces, so we can say 3 aces and 2 eights if we want. I want 3 aces out of how many aces? That's a group out of a group, right? I want a group out of a group. I want 3 aces out of 4 aces. Does the order of my aces matter? If I have an ace hearts first or an ace hearts last, does it make any difference at all? Not in most card games, right? It's not going to make a difference. So order doesn't matter. That's a combination. Now, if I also want 2 eights, 2 eights out of how many eights? That's going to be 4 choose 2. Same thing, order doesn't matter. 4 choose 3 is 4. 4 choose 2 is 6. Sometimes you see numbers often enough that you just remember what they are. You're not there yet, I get it, but 4 times 6 is 24. Okay, so we kind of put some stuff together. We put the fundamental counting principle together with combinations. And part C. How many such hands have exactly 2 hearts? This problem is very hard unless you get hyperliteral. Okay? When they say exactly 2 hearts, be hyperliteral. You're explaining this to a 6-year-old. What do they mean exactly when they say 2 hearts? 2 hearts and what? 3 what? 3 others. 3 others, 3 non-hearts, I guess you could say. Right? Because it could be diamonds or clubs or spades, right? So what that says literally is hyperliterally 2 hearts and 3 other cards, 3 non-hearts. Okay. So I like to write it as an and problem because it makes it pretty obvious what I'm going to do. And means times. So let's split it up into 2 smaller problems. Okay. I want 2 hearts out of how many hearts? How many hearts are there? There are 13 hearts. There are 13 of each suit. I want 2 hearts out of the 13 hearts in a deck. Okay? Order does not matter, so that's going to be 13, choose 2. And times. I also want 3 other cards, 3 non-hearts. So I want 3 cards out of how many other cards are there? How many? 39. Very good. 39. 39, choose 3 because order does not matter. 13, choose 2. Oops. 13, choose 2 is 78. 39, choose 3, 9,139. So we've got 78 times 9,139. $712,842. There are that many ways of getting a 5-card hand with exactly 2 hearts. Okay, that's a tough question, but it's kind of an interesting question, I think. But the tough question becomes an easier question by being hyperliteral. Use that. Don't forget about it. A lot of people that struggle with this lesson will completely ignore that little trick, that technique. How many such hands have cards of a single suit? Single suit. So I can think of a couple of different ways of answering this question, but either way, you've got to nail down what it means. What does a single suit mean? Very good. 5 hearts or 5 diamonds or 5 clubs or 5 spades. I don't know who said that, but that's very good. It usually takes people a lot longer to come up with that. But that's exactly what they're talking about. And that's probably the easiest way to think about this problem. But I've got something plus something plus something plus something. So if I want 5 hearts out of how many hearts? 13. So that's going to be 13, choose 5. But isn't it going to be the same thing for the diamonds and for the clubs and for the spades? Because there are 13 cards of each suit. 13, choose 5 is, I believe, 1287. So you've got 1287 here times 4, essentially. I'm not going to add those up. I'm going to multiply by 4 times 4. 5148. $51.48. All right. Now I'm going to show you a little bit higher level way to do this problem. Okay. So a higher level, if you can get to this, you're in great shape. But it's a lot harder to think about. I was not very good at this when I was in your shoes. But a different way of doing this problem is, let's say we have to choose a suit, and then we have to choose 5 cards. In order to do what they say, we have to choose a suit and then choose 5 cards. Imagine if you're dealing cards out and you're dealing to your buddy or something, you're trying to cheat. You're going to choose a suit and then you're going to choose the 5 cards that you're dealing out. All right, in order to have 5 cards of a single suit. That's called a. Anybody know what that's called, by the way? 5 cards of a single suit. All the cards of the same suit are. It's called a flush. But if I want to choose a suit and then choose 5 cards. Well, we've already done that. There are 13 of those cards. I guess I could have said values. Choose 5 values of cards. Out of the 13 different values there, we're choosing 5 of them. All right. But if I want to choose a suit, I got to choose like hearts out of the 4 suits. So I could say like 4 choose 1. I'm choosing 1 of the 4 suits, and I'm also choosing 5 of the 13 values. So it's going to be 4 times 1287 is the same thing. Both of those problems are doing the same way. The second way is a little bit higher level thinking, though. So if you can get there, then you're in awesome shape. Number 5, suppose 2 cans of soup are to be selected from 4 cans on a shelf: noodle, bean, mushroom, and tomato. Illustrate the difference between permutations and combinations by making 2 tree diagrams of these soups. Okay, so this is, I don't know, kind of a silly question. But we've got permutations. And so there's 4 cans, I'm picking 2. It's 2 out of 4, right? And 4p2 equals 4p2. Oh yeah, it's part of a factorial. 4 times 3 is 12, right? 4p2 is 12. Permutations are fairly easy to do in your head sometimes. Combinations, not as much. If I did combinations, it's 4c2. And 4c2 is going to be a different number. 6. Okay, so they want a tree diagram showing the difference between those 2 things. Permutation, order matters. Combination, order does not matter. So let's look at permutations first. All right, so we have to pick 2 cans of soup. So I'm going to pick the first can of soup, and my choices are noodle, bean, mushroom, tomato. So there's the first, first level of my tree diagram. And so then, after I pick noodle, let's say my first choice was noodle, then my second can either be bean, mushroom, or tomato, right? Noodle, bean, noodle, mushroom, noodle, tomato. But if my first choice was bean, then my second choice would either be noodle, mushroom, tomato. But if my first choice was mushroom, then second could be bean. Wait, why not start at noodle? Noodle, bean, tomato. Or I could choose tomato first and go noodle, bean, mushroom. That tree diagram shows me 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 different ways of picking 2 cans of soup where order matters. Notice noodle bean is different than bean noodle. That's 2 different things. Noodle bean, bean noodle, 2 different things, order matters. But now combinations, order does not matter. And so my first choice is still the same. I could go noodle, bean, mushroom, tomato. And then my second choice, if I went noodle first, I could go bean, mushroom, tomato. So same thing. But now the next one's going to be different slightly, because if I chose bean first, then bean noodle would be the exact same thing as noodle bean. If order does not matter, noodle bean, same thing, bean noodle, same thing. Okay, so I wouldn't go bean noodle, I'd just jump straight to bean mushroom or bean tomato. And then if mushroom was my first choice, then noodle mushroom has already been chosen, and bean mushroom has already been chosen. So really all we've got left is mushroom tomato. And so if you think about it, that's all the possibilities that there are. This really isn't going to be a thing, because if I try to do any branches after that tomato, then I've already got noodle tomato, bean tomato, mushroom tomato. I've already got a tomato showing. So there are 1, 2, 3, 4, 5, 6 different ways if order does not matter.